So, I recognize that so far it is very abstract, and I haven't given you any particular example. So now I would like to focus on these two examples that I mentioned before, the one of Fibonacci and the one of easy medians. And I want to start from the Fibonacci. Essentially, to understand really the structure of these matrices, the R and the F, it is useful to define a basis. And in particular, we will deal with a set of 4 Fibonacci unions. And I will impose that the overall have a trivial charge. This 0 is the identity of before. So overall, they are in the vacuum state. However, since they are 4, I am left with some inner degree of freedom. So I have possible states that tells me that these 2 Fibonacci fuse into the identity, and similarly these 2 Fibonacci fuse into the identity, so that identity times identity gives me the identity, and these states that I call 0. Whereas the other state, the other possibility is that these 2 Fibonacci unions fuse into a Fibonacci union. These other 2 Fibonacci unions fuse in another Fibonacci union in such a way that overall I still can have a vacuum charge, and I call this object 1. The other states of 4 Fibonacci unions have a different total charge. For example, I could consider a state in which the first 2 fuses into Fibonacci and the other 2 fuses into the vacuum, but then I would have that Fibonacci times the vacuum gives me Fibonacci. So I'm going out of this requirement that overall they are in the vacuum state. So you may think that I start from the vacuum, I nucleate 2 pairs of Fibonacci unions, and I want to describe this system. And this will provide the basis required, for example, to write down the braiding rules. So someone of you first asked me, but well, you are always basing yourself on conformal field theory. Actually, this is not fully true, because the NN models are a self-consistent theory, and this self-consistency is given by some precise requirements that the matrices F and R must fulfill. For example, the Young-Baxter equation can be written in terms of F and R matrices, and we will do it in a while, and it must be fulfilled, so it imposes some constraints. The trick is that once I decide what are all the fusion rules of my model, then I obtain that there is a set of equations called the pentagon equation, which allows me to calculate all the F matrices for the model. In particular, what is this constraint? Let us consider a system in which you have 4 ions fuse in some total topological charge. And as I told you, you have some inner structure. So you may label each state of this system by specifying what is the fusion outcome of the first 2 ions, and then the fusion outcome of the first 3 ions. But you may change bases. And we saw that the F matrices are the matrices that allow to change the basis in the case of 3 ions. So if I want to go from this base to this base, I may apply 2 different parts of these F matrices. In particular, here I can start to apply an F matrix for these 3 vertices, and move essentially these and attach it there. And then another for these 3 charges block, and end up here. Or I can do a different operation, which is a priori not equivalent, and move this segment here. So this is the F matrix of this small block, and then move this link here, which is the F matrix of this small block. And finally, apply a last, the third F matrix here. So, in principle, the result of this operator a priori is not the same. I must suppose that it is the same. And if I do it for all the possible 4 collections of 4 radians in my theory, I end up by specifying the F matrices apart for some free parameter which usually do not play any role. For example, for Fibonacci radians, you may in the end write down these equations so that the only non-trivial F matrix for the Fibonacci model is given by the case in which you have F tau, 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 and you have 3 indices here, so a system in which I have 3 Fibonacci radians that fuse overall in another Fibonacci radians, because in this case here I can have both 1 and tau, and also when I apply this F, I go in this basis where again I fuse tau and tau in this two-dimensional space. Whereas all the others, if you start to substitute some identity here, are simply, so you are left only with one state, so we become trivial. And if you build this equation for this F matrix, you obtain essentially these 2 constraints, you solve them, and you find that the F matrix has this form with this phi, which is the inverse of the Gaussian ratio, so the inverse of the quantum dimension of the Fibonacci. Actually, the fact that this term is always the inverse of the quantum dimension is true for the F matrix. So, this is to explain you that I can derive what is the structure of the F matrix starting from diffusion rules. Once I found the F matrix, I must somehow find what are the R matrices, and this can be done by considering other more complicated constraints that correspond somehow to the Young-Baxter equation. Before explaining you why this is the Young-Baxter equation, let us consider the fact that if I am in this situation where I have 2 Fibonacci radians and diffuse either in the vacuum or in tau, then I may represent the R matrix in a diagonal way. However, if I start to have, let's say, 3 radians here, and I am diagonal for the first 2 of them, and I want to represent what is the matrix that describe the exchange of this with that, I need some basis change, because in principle, if they do not fuse directly together, this R matrix in describing this exchange is no more diagonal. So I need to move from here to a new basis in which we are fusing together. Here I know that it is diagonal, and I move back to the original basis. So to explain it more carefully, let us say that I want to represent so I start with a system of 3 radians that are in this basis, which I label this total topological charge of the first 2 with X. I know that the exchange between A and B is diagonal in this basis, because it is diagonal in the total topological charge. And now I ask, what is the matrix which in this basis specified by the set of X, so my basis will be essentially the set of the X. I want to know what is the braiding transformation between B and C. Now, what happens is that this braiding will be diagonal in different bases, in which I have B, C, and Y here. So I may say, well, in this basis, this is diagonal, and I know how to write it. So I know that RBCY is an operation which must be diagonal. This is something proportional to the y prime, and there is some this is the diagonal on this basis. I apply a basis transformation, which is minus 1 f, this f, and this f has essentially the power to move in a different phase where we have x prime and x, and then by the superposition of this y. And this final matrix is the braiding operator in this basis, which describes the exchange of B and C. So I can call it R, B and C, and it is essentially the generator of the braiding. Now I can consider this exchange between A and B as a sigma 1, this exchange between B and C as a sigma 2, and I must be sure that the Young-Master equation is satisfied. So here, sigma 1, sigma 2, sigma 1 must be equal to sigma 2, sigma 1, sigma 2. And since I said that sigma 2 is represented by some f f minus 1, whereas sigma 1 is represented in the different R in principle, I can combine this equation and take constraints linking f and r's that allow me to evaluate possibly the braiding of this intersection. And so, in the basis that we choose before for Fibonaccian, this is clearly written in terms of these matrices. Essentially, consider the basis that we analyzed before, so A and A is equal, and the exchange of the first two unions is diagonal, because my basis is diagonal in this value of A, and in the states 0 and 1 that I wrote before, it reads in this way. Instead, the exchange between 2 and 3 is not diagonal anymore, because in principle it ends up in linear superposition with this A being either 0 or 1, and however, since all these particles are equal, it can be written as f sigma 1 f. I'm not putting the minus 1 here, because for Fibonacci unions f is equal to the minus 1, and you do your calculations and you obtain this matrix. Sigma 1 and sigma 3 are instead equal, because essentially I acquire the same phase if I braid counterclockwise these two particles, or if I braid counterclockwise these two particles, because I know that the two pairs must have the same topological charge always. And so, if you interpret these as a qubit, these are single qubit gates. And the interesting thing about Fibonacci unions is that these are strange rotations that generate a dense group covering SU2. What does it mean? It means that by combining a set of these operators, a very long set of these operators, I can approximate whatever unitary operator I want in SU2 with the required precision that, of course, fixes the length of this braid. Said it otherwise, you must consider, so these are the squares of the operators that we were considering before, and this sphere represents SU2 because SU2 can be defined in terms of an axis and an angular angle, so an angle of rotation. And essentially, if you consider what are the combinations of a single exchange of a single double exchange of particles inside my qubit, I have only 4 possibilities that appear as these 4 operators inside the sphere S2. But now, if I start to consider 2 exchanges like this one, 2 double exchanges like this one, the possibilities become 12 because I cannot undo what I did before. So essentially, the total number of these grades obtained by double exchanges scales with 3 to the n, and you may expect that therefore if I want to approximate something which is here, the corresponding error decreases in this way. And in particular, you may see that by increasing the number of double exchanges, I have an exponential number of operators that is going to cover the full S2 sphere in a dense way. So it's just a matter of deciding what is the required accuracy and then finding out what is the best grade which approximate the operator that you want to obtain. This is why Fibonaccianians could be very useful for quantum computation, because they really allow only through braidings to obtain whatever unitary operator you want. And that was true for single qubitanions. You have also recipes to obtain 2 qubitanions. So now I have 2 sets of 4 Fibonaccianions, and essentially I can entangle these 2 qubits by moving a pair of anions from the first qubit around the 2 pairs of the other qubit. And the interesting thing is that, of course, you obtain always operators of this kind, because if the first anion is in state 0, this is in the vacuum state, so I'm moving nothing around the rest, and I obtain that I must end in the identity. And this is true for the first two states that are 0, 0 and 0, 1. And in the same way, if the second qubit is in 0, these 2 anions fuse into the vacuum, these 2 anions fuse into the vacuum, and I'm moving a pair around this vacuum, and I do nothing. So everything also the third one. Whereas if these 2 pairs fuse in the Fibonacci, and also these pairs fuse in Fibonacci, I am in the 1-1 state, then I obtain something which is non-trivial. And in particular, I can map this problem to a problem where I have now 4 Fibonaccianions, because each of these pairs fuse in a single Fibonaccianion, and I want to approximate something which is proportional to the identity. Otherwise, I'm going out of my computational space, and with a certain degree of approximation, I can create, for example, this is a quantum Z operator which creates entanglement between the 2 qubits. So, more or less, this is the general idea about how we can do quantum computation with Fibonacci if we have ever reached some system with Fibonacci, and these are the main motors that you have to check if you're interested in this sort of topological quantum computation. And before going to the easing anions, I would like to point out some useful references. One very interactive reference is the lecture of John Braxton, and you can find it in his website. It has a mathematical flavor which is very strong. If you appreciate it, it's good. Then there is a more generic reference about topological quantum computation by Brandon Pacos, and Pacos also wrote a full book on topological quantum computation and anions, so you can take, of course, this book as a good reference. Finally, if you are interested in Fibonacci anions, this is a good introduction to the problem, also of chains, also more complicated things that I haven't the time to explain. So, are there questions so far? No. So, I guess that I can. in the remaining time, I would like to start considering the Isingenius and the Majorana modes. As I told you, the monobilian structure is the same. Isingenius and Majorana fermions are a bit easier to study than Fibonacci because we have a sort of representation in terms of operators, which is very helpful to understanding what are these variables and these matrices. In particular, I told you that usually once you think about Isingenius, you are thinking about fractional quantum mole. If you think about Majorana zero modes instead, you are thinking about one-dimensional structure in topological superconductors. The difference is that if the far I consider these R matrices that are the exchanges of anyons, in this case they will be Isingenius, and they are precisely defined with all the phases of well, I don't want to write this down now, but this is a matrix. Whereas for Majorana modes, you have only an abelian, a projective representation of the breakthrough. So for Majorana modes, we'll have the same non-abelian structure in terms of matrix, but a phase in front of it that you cannot absolutely control because it depends on the details of your system. So in one case, essentially, we maintain only the non-abelian structure, which is the one which is interesting, but we totally lose control of the abelian phases. Whereas in the case of Fibonaccianians, also the abelian components, so this will be multiplied by some operator in SU2, also this phase is precisely written, and it depends on the fact that these objects have an over4 charge. However, without entering too much in this detail of the distinction, the important thing is try to understand what are the states that comes out from a collection of these Isingenians. And in particular, you know that the fusion rule is this one, essentially, where I am anticipating you that this is a fermion, and I will consider it as a fermion to develop the calculation that we are going to do. Essentially, this means that if I have a collection of two of these Majorana modes or Isingenians, the pair of them can be found in two different states that correspond to have no fermions or have one fermion. In particular, therefore, I can define two C dagger and C related to this pair of Majorana fermions in such a way that, of course, C dagger C of 0 is equal to 0, actually, and C dagger C of 1 instead. So this is written 0, and this is 1. And however, it's interesting to note that essentially we may define these operators in C dagger, of course, the usual limitation, in terms of what I call real Majorana modes, which we have seen essentially from 1 times I over 2, and C dagger is equal to 1 plus I over 2 over 2. Where this operator is gamma, obey the twofold algebra, it is called E is equal to twice delta ij. So the absolute unless we are the same, and in this case we have that gamma square is equal to 1. And gamma is equal to minus 1. These are real objects. The important thing is that now we can rewrite this operator C in terms of this gamma 1 and gamma 2. And we obtain that C should be equal to 1 minus I gamma 1 gamma 2 over 2. This means that this object here is the fermionic parity of this pair of objects that we will imagine to be gamma 1 and gamma 2. And essentially, I have that I gamma 1 gamma 2 on the state 0 is equal to 0, and I gamma 1 gamma 2 on the state 1 is equal to minus 1. So that if I want to represent as a matrix this operator I gamma 1 gamma 2, this is a single set matrix. So, as we were considering before, since I'm interested in the nonlinear characteristic and the properties of these exchanges, two enums are not enough. I must add at least a third one to start adding two different breaking operators which do not connect with each other. And like in the case of Fibonacci enums, I actually consider 4 different manual angles, and I impose them to have an overall even fermionic parity. Overall, they must be the bottom sector. So I will have gamma 1, gamma 2, gamma 3, gamma 4, and I can represent, I choose the following basis to represent them, and I impose that here we have to zoom into the vacuum in such a way that the two possible states represented as before, essentially, gamma 4 must have the same fermionic parity for the two different pairs. So if here I have the vacuum, and also here I must have the vacuum, and this is the state that called 0. And instead, if here I have a fermion, also here I must have a fermion, and this is the state that called psi 1. So the interesting thing is to understand what is essentially the operator if I consider instead a fusion between gamma 2 and gamma 3 with respect to this basis. And the important thing, if you allow me for 1 second to use so the important thing is that I told you that I gamma 1 gamma 2 it is the sigma z also in this basis that I considered before, because the overall parity is 0 and the parties of these two pairs is always the same, and I obtain that just checking the fermionic parity of the first pair is enough to detect the state of the system. And I want to know what is this operator I gamma 2 gamma 3. And of course, using the algebra that I just raised, you see that this object anti-commutative. In particular, I can evaluate what happens if I start from the state 0, in which I apply this operator, and I want to estimate what is happening. Here, you see that essentially gamma 2 commutes with gamma 2, but anti-commutes with gamma 3, and then I obtain that this is equal to minus I gamma 2 gamma 3 of 0, but I know that this is an eigenstate of I gamma 1 gamma 2 divided value 1, so I just saying that this is equal to minus I gamma 2 gamma 3 eigenstate 0. So I conclude that I must conclude that I gamma 2 gamma 3 of the state 0 is equal to state 1. Because you see that it is an eigenvector of I gamma 1 gamma 2 with eigenvalue minus 1. And the same is true in reverse, so I gamma 2 gamma 3 of 1, this is equal to 0. So if I gamma 1 gamma 2 is equal to sigma z, I gamma 2 gamma 3 is equal to sigma x. And the basis transformation from one to the other, if you do things properly, you know, perhaps if you consider all this as free aliens, you obtain that the F matrix, sigma, 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 gamma, 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 this is the basis transformation from one basis to the other. So essentially it must correspond to this one. So in this particular case, where I can write down things in terms of this Newton operator, in terms of the Fock representation that I had before, to the fact that these are fermions, I obtain a simple way to evaluate the F matrix. Now let us consider the R matrix. And in particular, we want to understand what happens if we have a system gamma 1 and gamma 2 and I exchange them in this way. So we have two possible states. They either fuse into the vacuum, or nothing here, or they fuse into the fermion. And I must consider that twice this exchange, which is R gamma gamma square, is equal to a rotation of 2 pi. But the rotation of 2 pi for a system where there is a vacuum will need the identity and rotating nothing. If you rotate of 2 pi a fermion, since a fermion is a spin 1 alpha, you obtain a phase which is pi. So when you write down the R gamma gamma, which is into I, as a phase which will be I times in the case in which they fuse to I, you will have the theta of I, which is 0, minus twice some other phase that is the topological spin of the gamma set, that will not indicate it's not in phase. And instead, here I will have that once I have R gamma gamma, which fuses into epsilon, here this will be to the I, so I'm doing this squared, and this will be this pi minus 2 theta gamma. If you now forget a little bit about this phase 2 theta gamma, which is however in common with the two matrices, you obtain that the matrix R gamma gamma is equal to VI pi over 4 sigma z, and I'm essentially neglecting some overall phase again, because you see that here we have essentially 1 and I, because it was alpha of this rotation, this is squared, and so that if I collect the I pi over 4, I can write this as minus I pi over 4, plus I pi over 4, and I obtain that this is my rotation. The size that I have also to add linear phase, which is this theta gamma. So this is the rotation, the exchange matrix in the case in which I am considering a diagonal basis. So essentially, in the two states that I wrote at the beginning, this corresponds to this exchange. Now I can consider what happens instead with this exchange, which is no more diagonal in the previous base, but we calculated what is the basis transformation between the two, so that if I call this sigma 1, then sigma 2, because sigma 1 is exactly this one, then sigma 2 matrix will be minus 1, sigma 1, and step. And apart for so neglecting these phases, which are just the root phases, I get the I pi over 4 sigma x. By the way, I remember that you can write sigma x and sigma z also in terms of my ground operators. So, the two things, of course, sigma 1 and sigma 2, they do not commute, but they must obey the Young-Baxter equation. And furthermore, we have that an interesting thing is that, so we have that what was sigma 1, sigma 2, sigma 1 is equal to sigma 2, sigma 1, sigma 2, and I can also tell you that for coincidence, this is not a rule of fluidity energy model. This corresponds to fluidity F. And instead, I have that if I apply sigma 2 twice, so I calculate sigma 2 squared, this is equal to sigma x. Why not in the quantum computation language? And this is interesting. Furthermore, you obtain also that sigma 1 to the fourth power is equal to sigma 2 to the fourth power, which is equal to the identity, because you see that this over 4, which simplifies. So apart for, as usual, hidden phases that I consider this however, this fact that two exchanges of these Majorana firm, this Majorana modes, or this ingenious gives me a knot is pretty important from the experimental point of view. Namely, if you want to demonstrate that these objects have a nonlinear statistics, you should start from a system in which you can initialize your state written in this way. So you have that, you know that gamma 1 and gamma 2, they are in a particular state, which can be either 0 or 1, and then you will have some gamma 3, gamma 4 there. Then you start to exchange these two states, and you obtain that if you were in 0, then with first exchange, so an application of the operator sigma 2, you end up in 0 plus minus over square root of 2. And instead, if you are in 1, you end up in 0 minus 1 over square root of 2. So if you have some tool in your lab to to do this exchange, you have that after one exchange, you have half of the probability of being E0 and half of the probability of being E1 if at the beginning the system was initialized in either of the state. If you do then the second rotation here, in the same kind, you obtain that here you are flipping the state. So here you end up in 1, and here you end up in 0 after the second rotation cycle. So essentially you have a sort of experimental signature to detect these nonabelian statistics, because I'm telling you that I'm starting from these Majorana modes and they have a fermionic, given fermionic parity, so if using a fermion and 0. Then I'm just interchanging gamma 2 and gamma 3 twice without touching gamma 1, and strangely enough, in the end, I've transferred a fermion from here to there, just as an effect of this double exchange. And in principle, for topological superconductors, this could be a valuable route, a generic idea at least, to demonstrate that the exchange of these two objects, two exchanges, may affect the degree of freedom of two different objects. That is more or less the idea of nonlinear statistics. So, about Majorana modes, I can start to introduce the subject, and I have to tell you that on the computational point of view, this representation of the gamma is one of the most important tools that you have to deal with them. But the trick is that essentially you want to have a system which is usually some superconducting system, and tomorrow we will see it better, in which you obtain Majorana modes that are far enough not to be interacting, so that this distance must somehow be great with respect to the coherence distance of this superconductor. And under this assumption, so if they are localized, very well localized in two different places, you obtain essentially in this case it will be the gamma 1 and gamma 2 commute, and we will show tomorrow that we can engineer systems in which these operators gamma, which are here and the gamma squared is equal to 1, can be obtained as symmetries of some Hamiltonian. So as operators that do not change the energy of your Hamiltonian. They are called zero mode for this way. And it is important to note that usually in these superconducting structures, they always arise in some domain mode, in some interface between what is called a topological phase and a normal phase. And we see through some simple example tomorrow how this can be realized with a microscopic Hamiltonian. So the idea is that if you want to engineer this object in a lab in such a way that you can apply these braidings, you either must be able to move them around in some strange geometry in which you can move this domain wall along this is called T-junction, in such a way that if I want to exchange gamma 1 and gamma 2, I just start to move this domain wall, leading back the trivial phase down here, and then move the other domain wall here, and then back again, in such a way that I exchange these by doing a sort of maneuver around this T-junction. And otherwise, another possible recipe is to have them interacting and being able to provide interaction. And this is an effect that you will have time tomorrow to see, otherwise but I want to do some generic idea. However, the trick is that if you have 4 of these modes, 1, 2, 3, 4, and you switch on a strong interaction here, you are saying that these 2 are fused in a given fermionic party, for example, in the vacuum sector. And then you can observe what happens to this subsystem. And if you apply the local operators inside this system, you cannot change the overall fermionic parity. So you cannot change essentially the fusion between this gamma 1 or gamma left and this gamma right, because the total fermionic parity at this point is the vacuum times the 2 of them. So we have again 2 states where these are fused into the vacuum or in the psi sector, in the fermionic sector, so that we can start to increase this interaction and decrease this interaction without affecting the state. But essentially the effect of this operation, adiabatic operation, is to end up in a system where I copied the information of gamma left here, or I teleported it here somehow. I'm not really moving the 4 Majorana modes that are always stick together, but I'm just applying the interactions. And I can repeat these 3 alien moves essentially, also on top of here, to move gamma higher here, by switching this interaction, and causing that these are fusing into the vacuum. And finally, I go back to the initial configuration where I move this gamma L here, and I'm again fusing the strong way these 2 auxiliary Majorana fermions. And the result can be calculated through a barometric computation or other interesting tricks, and you obtain that the result of this process is exactly this pi over 14 Z that we were considering before, up to some barometrics that you cannot really control. That's why you usually say that Majorana modes in topological superconductors provide you a projective representation of the braid group, because all the sigmas can be represented up to a phase that you cannot control. But still, apart from these phases, all the things that are related with the nonlinear characters, like this is the interesting part. The last comment that I want to do is that differently from Fibonacci aliens, the Majorana modes or the Ising aliens do not provide you enough power to get universal quantum computation. This is because we saw that the two rotations that we are doing are e to the I pi over 4 sigma z and e to the I pi over 4 sigma x. And you may verify that these are a rotation of an angle pi over 2 around the axis z, and this is a rotation of an angle pi over 2 around the x-axis. But if you combine these 2 elements, you obtain a closed group. So you obtain the group of the symmetries of the cube, which is not enough to densely populate SU2. So if I replot the sphere with these objects, I will obtain that by doing braidings of the Majorana only, in the end I will obtain only a finite number of elements, but I cannot cover the sphere uniformly. So I will have huge errors when I try to approximate a random unitary operator with one of these. So if we want to do universal quantum computation with Majorana aliens or Majorana modes, we must somehow go beyond these schemes which consider only braidings, and there are several techniques to do that. The most famous is called distillation, but I will explain it here. may ask. And furthermore, to obtain two qubit gates, I need to do measurements. I think that I can end here and thank you.
Grazie.